Okay, hi everyone. I'm Alex, and I will introduce Statistical Dialogue Systems in this course. So, you have like 4 days to talk about synthesis. 3 hours is not enough to talk about everything in dialogue. So my goal is here to give you an overview, to give you an idea and a sense of the challenges and the problems that are involved, and how people go about solving some of these. A little bit about myself. So I'm from Athens, where I did the first part of my studies there. Then I did my PhD in a research institute in Athens called Demokritos, where they do language and dialogue, in collaboration with a university in Texas called UT Arlington, where they do engineering and robotics and things like that. So we kind of fused the two, and the application was multimodal adaptive dialogue systems. Adaptive meaning we have people with disabilities, mental or physical disabilities or other forms of difficulties, and the system had to adapt both in the input and in the output. I then joined the Articulab at CMU, and we did socially skilled virtual agents. So there the idea is how can you design an agent that can build, for example, a long-term relationship with people. That is not just a question answering machine, but can actually do meaningful things and, with social skills. Then I joined Toshiba Research, and there we worked primarily on goal-oriented dialogue systems. So more kind of transactional systems that you do like for flight booking, customer support, and things like that. And now I'm at Uber, where we have a conversational AI team, and we work on a lot of challenges and problems. Some of these I can talk, some of these I can't, but we do a lot of good research. We have a very strong AI team that does a lot of things like planning and scheduling and forecasting and many other basic research problems. So like I said, in the first part I will introduce conversational agents, a little bit of history and all of the moving parts that are involved. Then we'll have a small break, and then I will talk about the current approaches and a little bit of deep learning, not into too many details because there's many components, but again kind of giving you an idea and an overview, and introducing the Plato dialogue system, which I have been developing for the past few months, and we'll use that for the hands-on on the final session. So I'm sure you're familiar with most of these things. Nowadays, almost any kind of tech company has a conversational agent, and also many other hardware companies or non-tech companies are moving into this field. So we have agents like Siri, Google Assistant, Cortana, Facebook M, Samsung Bixby, Alexa, of course, Watson, and many more. Some of these designed for different purposes, like, be an assistant on your phone or do business analytics or other kind of things. But a lot of them have similar challenges that they need to solve, like technical challenges and other challenges. And of course, we see them into more and more devices and more specialization. So we have smart speakers, we have smart devices, we have hardware companies or, Adobe who wants to put conversation into Photoshop, so you can say something like remove the cat or make the sky bluer, and it will know how to do it. And we have older companies that have been doing NLP more than dialogue, I guess. And challenges there are if you want to summarize the news very quickly for somebody to make a decision, accuracy matters and how you actually do that and avoid fake news and all of these things, biases. And other systems, for example, in cars have different challenges like radio playing or the window is down, there's a lot of music, a couple of different speakers. And of course, besides all of these, there's a lot of speech and language startups that are coming up. Almost every other PhD student makes a startup. But these are more, speech-based interactions. There is a whole other world of conversational agents that can have bodies, and we call them embodied conversational agents. And these can be virtual or physical. So this is one dimension. The other dimension is how much they resemble humans. And so you can have a virtual agent like, I think Ellie is called, who is a psychologist, or Sarah, who is a virtual personal assistant. And in these cases, we have different kinds of challenges, like how you synchronize the speech with the words and the gestures and the eye contact and all of these things so that the interaction isn't weird, and how you design an agent, like, what are they wearing, ethnicity, and all of these things that can make a big difference. Or you can make them a little bit more cartoony, and that reduces the expectations that users have for intelligence of these agents. And then moving, to agents that have a physical presence. There we have other kinds of challenges, like how close do we go to the user, design the robot safely so that we don't hit the user, so that it's not intimidating, it doesn't look like a big laundry machine. And we have, again, robots that look like computers or look more human but cute or look entirely human. So this is Toshiba's humanoid robot. This is David Hansen, a guy from Texas who is half artist, half computer scientist. So he made a lot of very realistic robots, but the motors inside were not very good at the time, at least, too many noises. And then Ishiguro, of course, who made himself. This is the professor, this is the robot. And these things then, there's this uncanny valley that the more the robot resembles a human, there is a place where if it resembles a human too much, it's creepy. If it's not entirely human, but it's kind of human. And so these are kind of there at that point, but maybe moving on as the technology moves on. So then we will have probably other kinds of things to discuss, like ethics. So now I wanted to show you a little bit a demo from last year, and I hope this can play. This is the Google Duplex. So Google, in 2018, trained a conversational agent to be a user. And this means that, instead of training a conversational agent to be taking orders from a restaurant, you are training one to pretend to be the user, so making a reservation at a restaurant. And that can be useful because you can grab your phone and say, hey, Google, book me a restaurant for 4. And the conversational agent will call the restaurant, a human will pick up, and then, they'll make the booking. And let's see. Yeah, we hear the...
I'd like to reserve a table for Wednesday the 7th.
For 7 people?
It's for 4 people.
4 people? When?
Wednesday at 6 p.m.
Actually, we need there for after 5 people. For people, you can come.
How long is the wait usually to be seated?
When, tomorrow or weekday or?
For next Wednesday, 7th.
Oh, no, it's not too busy. You can come for 4 people, okay?
Oh, I gotcha. Thanks.
Okay.
So that's what they presented. But then, of course, things don't always go as planned sometimes. So this is when things can go wrong.
Hello? Hi, can I talk to Diane, please?
Speaking.
Hi, Diane. I'm calling on behalf of John to schedule an appointment. For what? The appointment for you to come pick up your belongings from John's apartment. Excuse me? John would like you to remove your belongings from his apartment. What are you talking about? I'm very sorry, but John has decided to enter. Joe, put John on the phone. I'm sorry, John's not currently available. What? Where is John? I cannot believe this. This is bullshit. Mm-hmm. How does 10 a.m. Oh, if 10 a.m. is not available, then it's up for you. Fuck you! Hello? Hi, can I talk to Diane, please?
Okay, so this was a mock video, of course, that you can see. Things going wrong. And also I wanted to mention something that we have been working on. I guess some of the things are a little bit weird. We call it a baby duplex because it's a very, very downsized version of that, but it's, done with Plato, the system you're going to see later. And what we did here is we took like a standard domain in Dialogue, which is a restaurant information system, and we trained two agents, one that is an information provider and one that is an information seeker. So the user and the system trained concurrently as they talk to each other, and the system learned to provide information of how to, what kind of restaurants are there, and the user learns to how they can, access that information, how they can request the information. These are the kinds of dialogues that we can generate. They are not very complicated, but we generate things word for word. And so the data set also is not very big. I think it's 1,500 dialogues or so, maybe a little bit more. So, just having coherent sentences in both sides is very promising for us. And so, I've shown you a little bit of the state of the art and the things that we can do, but do you think we are pioneers? People have been dreaming about robots, especially on this island on Crete, since 400 BC. And this is a depiction of Talos, a bronze robot protector of Crete. And people have been, they didn't build it, but they were sure talking about it. Then many years later, Thomas Edison came up with this doll, which had recordings, so it's a little bit of synthesis, but not, not exactly. And then how long do you think it took to get the first dialogue system out? So it was the early 20s, and this is Radio Rex. It's a full dialogue system with ASR, language modeling, and of course dialogue. So what happens is if you say Rex really loudly, the little dog will come out. So there's, one word understanding, basically if you go over a threshold with your voice, and one action, Rex coming out, but it's a full dialogue system. And then later, there's been a lot of progress, I guess, in the last 30 years, starting from the early 90s with keyword spotting systems. And these systems will tell you what the options are. Like here they say, please say collect, calling card, person, third number, and so on. And as we progress through the years, these systems become more intelligent, and they don't only do keyword spotting, but they do also intent recognition. You can say, we want to change our phone line, which there may be like 500 different ways of saying that, but the system would still work. Multimodal systems, personal assistants, and coming up to 2018 and 19 with all of these devices and agents and assistants that work across devices on watches, fridges, cars, and everything. So all of these companies that have been working on this are probably onto something. Speech and language is a very good form of communication, and if you think about it, people have been doing it for thousands of years. But why so late compared to the rest of computer science? This form of communication is very different than others, and so especially speech. So in speech, there are many disfluencies that we as people are trained to ignore. So we do a lot of disfluencies like or just saying like, all of these things. But for a system, if you get these words, all these signals, you have to learn how to handle them. Word phrase repetitions, false starts or restarts, so you start saying something and then you correct yourself, so the system needs to know which part of the utterance has the correct value. The problem is ill-defined, so there's a tremendous amount of common ground, common knowledge that is assumed by the people talking to the system. For example, a chair has 4 legs, or something, a car can drive on the road but not in the sea, and things like that. There's a lot of noise in the channel, like other people talking, and you need to say, who is talking and who said what. Bad qualities in the hardware, like in the phone line, or there is music playing, and all of these other things. One partial solution in terms of dialogue that we can do is grounding. So we can implicitly or explicitly confirm what the user says. So basically we just ask them back, did you mean this, or I thought you said that, and all these kind of things. Then if we have a conversational agent, things like turn taking are important. So when the user speaks and when the system speaks is important. And it's important to design the strategy that we will use for interruptions, or if we will allow interruptions, for the whole experience. So margins and interruptions, and the system knowing when to interrupt the user. For example, if it is a car and you detect a collision, maybe you want to interrupt them, but maybe not in other cases. And then paralinguistic information. So communication is not only text and speech. There's the things like how we say them, the pauses that we make, the emphasis that we put on, and the gestures that we do, and of course the context around everything that we say. And this may sound easy for humans, but just getting the data to train a system is extremely hard. And another thing is that because we assume so much of the common knowledge, if we have a few words changed, like a not, if we put not in a sentence, it can change the meaning dramatically. Similar to like the adversarial attacks we have on image networks. And then another thing is the more intelligent we make the system, the higher the expectations of the users are. So, if the TTS is very good, the people will expect higher intelligence, but that can be very hard from the conversational perspective. So how have we been going about these problems? To build an agent that can have human-machine dialogue, there's a lot of fields that need to come together, research fields, in order to do this. One of them is dialogue theory, which tells us how people talk to each other, and the kinds of information that they exchange, what are the packets of information, and what are the discourse obligations. For example, if I ask a question, I expect somebody to answer, otherwise it may be impolite. We have language technology that models these language, like grammar or language models or other things that are more at a practical level of how we can actually model this and create algorithms. We have a lot of mathematics. So how we can create computational models based on these things and train them on data. We have human interaction principles that tells us, what if we have 4 people talking to each other? Who takes the turn? When is it polite? How does, eye gaze matter? When do we interrupt people or not? And social sciences, so culture matters a lot here. So something that is impolite in one culture may be extremely offensive. Something that's polite in one culture may be extremely offensive in other cultures, like interrupting them or something like that, or the length of the pauses may be different. And all of these things need to be modeled into the assistant, but of course the application also plays a very big role. So if we have, for example, assistive living, there you may have people who are by definition not competent with technology. So maybe they are the elderly, they're not familiar, or maybe they are wounded or injured somehow and they cannot type. So we have all these multiple modalities that need to be synchronized in the input and then decide what is the best way to convey the information appropriately. It may not be speech or language, maybe showing an image. Other applications like education or training, for this we need, we have a longer relationship with the system. It's not just one-shot dialogue that you ask a question and you get an answer, but you have a discussion. You need to keep track of history, what has been said in this dialogue, in the previous dialogues, what has the user learned so far. And then robotics, of course, you have the physical interaction. You expect more things sometimes, or you need to make sure that latencies are observed, and many, many other things, as I mentioned before. So all of these things come together to build an intelligent agent. Now, zooming in a little bit, there's three main components in a conversational agent: understanding, dialogue, and cognition. And usually, depending on which field you're coming from, you think that your own is more important. So people who do understanding think that if you do understanding and get the intents and everything correctly, then dialogue and AI is kind of a trivial problem. If you do dialogue, you think that understanding is kind of keyword spotting, and you can always do it, and you can handle uncertainty in the dialogue, which is the biggest problem. How do you convey the information? How do you do the turn taking? And AI is just like a backend call that you get your information from. And if you are an AI person, of course, you think that this is the biggest challenge of everything. And dialogue is just how we communicate with people. So it's just an interface to people, and then you just need to solve the actual problem, which may be scheduling or optimizing something and so on. And so far we've been talking about dialogue systems, but the last couple of years a new term has been coined, conversational AI. So guess which group did that? And that's mostly due to the deep learning invasion everywhere. Let's see a little bit of the conversational architecture. I showed this a couple of times, so you'll be familiar. So let's see that we have a flight booking system, and the user says, I'm flying from Austin. First step is to do language understanding, so extract the meaning of what the user said, given our application. And then we go to state tracking. We mean dialogue state tracking. That keeps track of the information so far, what has been said in the dialogue so far by the user and by the system. Then usually we have an API call. Maybe we query a database of available flights. We get all of the results, and then we have an action selector, which selects the intent and the meaning that the system needs to convey to the user, which then goes to language generation that actually generates the text. And in this case, we got too many results, and we say, where are you flying to? Now some other basic concepts. Dialogue turn is sort of the unit, time unit in dialogue systems, and it is one person talking. Now, sometimes we say that it's one person talking and another person responding, but from the agent's perspective, the user says something and it is going through the full cycle of the pipeline until the system says something else. So it mainly has the utterance after the speech recognition part. Then we have dialogue acts, which have usually this form: communication act, and then attribute, operator, and value. And this means this could be, inform price equals cheap, time equals early, or confirm that the price is less than 150. And this can also be intents. For example, book. Depending on the application you are designing, it could be, to navigate somewhere, or to book a trip, or to search for a flight. So sometimes we call these intents. But let's say it's their communication acts. I will have dialogue history, which keeps track of what has been said so far in all of the interactions. Maybe, it's kind of a little bit vaguer, but the dialogue state contains relevant parts of the history that we need to make a decision. So the state should contain anything that the system needs to produce the next intent and the next utterance. And the domain, of course, is what the conversation is about. It could be flight booking, it could be navigation around the street or something like that. We can have, of course, multi-domain systems and sort of open domain, not exactly open domain, but systems that can talk about many things. And a core formulation, mostly in the research, is slot filling systems, where the idea is that you want to make a query to a database, so you need to extract all of the relevant information before you can make the query. So let's say it's a tuple of slots, values, actions, and database. So the set of slots has more or less a one-on-one mapping to attributes in the database. May not be one-on-one, but let's say that it's attributes in the database. Values is the available values that a slot can take. For example, if it's origin or destination, it will be cities or airports. Actions is a set of dialogue actions that the user can make or the system can make. For example, inform, request, or confirm. And a database contains the actual flights or restaurants or hotels or whatever it is we're looking for. And for example, here we have the Cambridge restaurants where we have some slots, for example, food or price or area, name, and so on. And each of these has their own values. Yeah, an important thing that we do, sorry that my slides are designed for that computer, so it's kind of, so it's the system requestable slots. So for example, I guess traditionally it has been hard to solve this problem, so we try to make the problem smaller. And so we defined what we call system requestable slots, which means that a user would never say, I want a hotel that has this phone number. It doesn't make sense, so we remove that from our modeling. And any slot that makes a sense for, to query the database with a value, for example, food, area, name, or maybe address, we call these system requestable. And the rest of them we call user requestable, because the user can always ask when we give them the restaurant or the hotel, they always ask what's the phone number, what's the address, and the system needs to be able to handle these things. So this is an example. User can say I'm looking for a hotel in Heraklion with free parking and at least 3 stars. So somehow we do language understanding and we extract the values of slots. So the type is hotel, location Heraklion, services, and stars. And we use these things. Now this is one turn, but you can imagine this can be a dialogue. And basically we use these to form a query to a database, retrieve the results, and then give the user the hotel that they want. But of course, in practice, this doesn't really happen. So users can say all sorts of different things that you never imagined. Like, what about the one with the pool, which means referring to hotels that you mentioned before, and you need to keep track of these, which of them had pools or not. How much was breakfast there? So you need to compare, maybe, and all these other things that may seem simple, but are not really that simple. Some dialogue act examples. Here, for example, hi, I'm looking for somewhere to eat. This is a hello action, and we have some arguments. Then you're looking for a restaurant. This is an implicit confirmation because we're not asking for that. What type of food would you like? So we are requesting the type, we are confirming the restaurant, the type is restaurant, and we're asking for food, and so on. So traditionally in dialogue, we need to annotate corpora, human-to-human corpora with this kind of acts so we can train our systems. And there's plenty of dialogue domains for information seeking or slot filling dialogues like Cambridge restaurants, hotels, or laptops, and so on. I won't go into details here. And there's more data sets that have come up in the past couple of years, maybe 2-3 years, that are start to be a little bit more complex, like the frames dataset is human-to-human on travel booking, and the goal there is, one person plays the role of someone who wants to plan family vacation, so you have constraints, like number of people, do you have kids or not, the destination, the days, the flexibility, and the idea is how can the agent learn to negotiate a little bit on the prices or the constraints that are kind of flexible with the user to provide a better package. And many other data sets that you can explore. A lot of them are annotated, a lot of them are just text. So let's go in a little bit deeper just to get some of the basics. So if we have spoken communication, the user can say, I'm flying from Austin. So we get a speech signal, and this is translated into, goes through speech recognition, and we have a hypothesis or a list of hypotheses. For example, I'm flying from Austin, or I'm flying from Boston, and each of these has a score, not necessarily a probability, but let's say it's a score of how confident the recognizer is that the user said that. And this is what we use, this input, to try to extract the meaning of what the user said. And depending on our application, we can do either shallow understanding or deeper understanding. So for slot filling systems, we're more on this side. So we basically care about getting from and Austin correct, so you know that it is the origin and the city is correct. You don't really care about other things. And then, if you have something that is a tutor and you have to understand mathematical concepts and stuff, then you may need to do a little bit deeper understanding, part of speech tagging or, other kinds of parsing. If you have a chatbot that's text to text, then you're probably even further here. The next step is dialogue state tracking, where we take, so the language understanding component will again output a list of hypotheses with confidence scores. And so we need to do dialogue state tracking. And how this works is we get these hypotheses from language understanding that are dialogue acts. It could be a list of dialogue acts with a score. And let's say we're tracking the slot destination, so we have no information about the destination here, so these are all of the values, and this could be, for example, the probability. And then the dialogue moves on, and the user says Austin, but we think that maybe they said Boston, and we may think that they did destination, a request for a destination. So because they mentioned Austin and Boston, then these get some probability. Maybe there was some noise in the channel, so other cities get some probability. And then probably in the system there is a rule that says if you have, too many values that are close to each other, probably do a confirmation. So we do that, and then the user repeats Austin, and then, this gets a higher probability. So this is kind of a rough overview of how we track it, or how we used to track it, because with deep learning it may not be very, those methods may not be very relevant. And then the same principle applies to intent. So, intent here we have inform and request. We need to do two things, to detect the intent and to detect the slots with their arguments, right? So this is kind of, two kind of problems that we have there. And then dialogue management, traditionally, I guess initially it used to be with finite state machines, because in production systems it's hard to train and probably trust a statistical system, at least in the early days. So this is an example of a system that will give you the phone number or the, email of a person or a lab. And this is your state where you're at in the dialogue. If the system says, you're looking for a person or a lab, you say a person and you move here. And then there's no way to move back, of course. And then you have to say the name of the person and extension or email. So this has pros and cons. The pros are that it's easy to interpret and it's very predictable to what the system will do and understandable by humans. But on the other side, this can get really messy very quickly and very hard to debug the behavior. Even though you understand it, it's very hard to debug it. And yes, and also does not adapt if you want to hop from here to here. You can't adapt, you can't recover from errors. So the way that we are solving this problem is with reinforcement learning. So this is a video of a real-time or online reinforcement learning, where this is a goalkeeper, and as you throw the ball, it learns to not let it through these sides, I guess. So the main idea here is that you have an agent that interacts with the environment, and it makes an action. It could move or say something, and it receives some feedback, and it gets, it observes its new surroundings in new state. So in traditional, let's say supervised learning, it's something like making a prediction and something like getting a label, not exactly the same, but conceptually kind of close. So the idea is the agent interacts with the environment, gets some feedback, and learns to associate the state that it is in with good actions that can lead to achieving the goal. And so core concepts here are a policy or a behavior, which is a way of choosing an action from any given state. And the objective of reinforcement learning is to learn a good policy, a policy that will optimize our objectives. And the method that we use is to explore, see, states, actions, and rewards we got, and try to take advantage of that to learn good policies. So this is an algorithm that came out of the Uber AI labs, and this is called Go Explore. It solves some problems that were previously not solved from AI algorithms. And the main idea is that it's a new way of exploring the space to get very good policies that you then use to train your agent. And let's talk a little bit about Markov decision processes or sequential decision making. So to make reinforcement learning work, we need this kind of formulation. And so let's say, for example, we have a lecturer who is paid $20,000 a year, and we want to calculate, how much they can make in their lifetime. So very naively, we could just sum the amount of money that they get over the years, and they will be rich in no time. But what's wrong with this reasoning? Besides taxes, rewards in the future are not worth the same as they are today. So $20,000 5 years from now don't have the same buying power or same value as they have today. And also, things may go wrong. You may have different kind of expenses that are not captured into our very simple model here. So the way to go around this is to introduce the concept of discounted rewards. So let's say that money 1 year from now is worth 90% of today's value. So then n years from now it will be worth 0.9 to the nth. And so 0.9 here is our discount factor. And the idea is to calculate the lecturer's future discounted sum of rewards to better reflect what the value of the lecturer's wealth will be a few years from now in the future. And we can just sum, the reward that he gets now plus 0.9 with the reward 1 year from now, and so on. And so this can tell us what the reward is if things go smoothly, but of course things may change, right? So the lecturer can have changes in his academic life or her academic life. For example, she can be fired and end up on the street and just live on benefits or make $5,000 a year, or he may remain a lecturer for the rest of his life, still making $20,000 a year, or may be promoted to tenure professor, making $80,000 per year. And of course, we can have other life changes. For example, the lecturer decides to go for a successful startup, sells the startup, and makes $5 million a year. Or on the other hand, the professor can just die and make zero money for the rest of his life. So the way that we capture this is we can capture this as a state. We can model the state of transitions here. So we have the starting state, our professor that makes 20,000. The numbers are a little bit different. These are from an older presentation. But so we have transitions that can go from some states to other states. We don't need to have all transitions from one state to other states, but each of them has a probability. So the professor can be tenured, can sell the startup, can die from any point in time, can end up unemployed, and so on. And so again, the idea is how do we find the best path through this graph so that we can maximize the expected, the expected sum of the discounted rewards. And again, the policy will tell us, given any state, any of these states, what is the best action to take so that we can maximize the reward in the future, not necessarily in the short term. So the MDP consists of a set of states, which are, for example, these 5 states, a set of actions. So here I don't have the actions, but let's say, get promoted will get you there, or do something to get promoted. A transition function which models these probabilities, or you make an action, what's the probability that you end up in another state, and a discount factor. And so we apply this modeling on dialogue. This is a fairly old idea, about 30 years old. And the idea is that in dialogue, we have the dialogue state and the action is the dialogue action. So the system will say something and it will be in a different state. The user will say something and the system must observe what the user says. So let's say we have a hotel booking assistant and we have 2 terminal states, success or failure. We assign high reward for success and no reward for failure. So, we can do things like ask for more information. We still have not enough information. While we loop in this state, we get some penalties, but then sometimes finally we get enough information to book the hotel, and hopefully we'll get to the successful state. So the idea is to find the shortest path that accumulates the minimum number of penalties to get us to the successful state, booking a hotel for the user. And the policy will tell us, given any state, what is the appropriate thing to say, right? So in the dialogue system formulation, the agent actually is here is the dialogue manager or the dialogue policy, and we have a dialogue state, a dialogue action, and we need to define the reward. So that's a kind of a tricky problem because we, in the lab we can define whatever we want, but in reality we don't really have some feedback. If the user knew what they wanted, they probably wouldn't call the system, they would go book online, right? So fine-tuning the reward is also a tricky problem. And we can train it with reinforcement learning algorithms. There's a multitude of those. We can get data from human to human or human to machine or simulation. We'll see a little bit more about this later. Traditionally, usually reinforcement learning needs a lot of examples. Now, a little bit more details, I guess. So reinforcement learning, optimal control are kind of similar, but for optimal control we know the dynamics of the environments, but there are some disadvantages, I guess. We can't really solve very big MDPs analytically, and the idea is we explore the state action space and exploit.
Just an interruption. First of all, you can ask questions. This is school, right? So, in order to do that, there are these microphones here. You put speak, then you ask questions so everybody can hear you. Then when you are done, then press again. Okay? So, feel free to ask questions. Don't let Alex play this game. Ask questions. Make his life more difficult.
So we have two key concepts here, the value function and quality function. So this will tell us what future rewards we can expect if we are from this state. So it's the expectation of the sum of the discounted rewards, given that we start from this state, looking into the future. And the Q function will tell us the same thing, but if we start from this state and take this initial action. So this is useful, if say we have a way of having this function, then we can simply do an argmax and say what is the action that maximizes this thing given this state, and that's our policy. And that's what we try to learn usually. This is a very simple algorithm that we can see also in the hands-on. So it's called Q-learning, and the idea is that this is our learning rate, so we keep part of what we know from before, and then the reward that we got plus the discount of what, I guess, the best possible thing we can do in the future, right? So this will give us an estimate of if everything goes perfectly well, and given that the reward that we got, how good is this state? And over time, and if we iterate, this becomes more true. Now, one thing about reinforcement learning is that we need a lot of data, and in dialogue, we didn't used to have many data, or we couldn't simply get data because they're personal data from customers. And so one way to go around it, besides simplifying the problem, is to develop simulated users. So we develop simulated users that, this is one of the traditional, I guess, very well-known architectures that has an agenda. You can think of the agenda as a stack, and the idea is we have a domain, let's say hotels. We can sample a goal. Let's say that the user wants an expensive hotel at the center of town. Then we have a way of producing some dialogue acts like hello, inform, request, 3 stars, and whatever. And we put this into the stack. And then when the simulated user wants to talk, basically pops one or more actions, and this is what the simulator says to the system. We need to do some housekeeping to maintain consistency here, but then when the agent speaks back, we have some probabilistic rules. Given what the agent may say, how many stars do you want? So then we have some rules that tells us, do we need to push more actions into the agenda? In the next turn, again, we pop some actions. And this is a very simple way for us to jumpstart learning. You know, these policies are not realistic and usually don't capture the linguistic variability of what people say, but they're a good way to get the system started. So we learn a good policy like this, and then we can talk to people, we can let the system talk with people and, you know, fine-tune or do online learning. Now a few more things, I guess. All of the above kind of assume that we can observe the state exactly, but in reality there's a lot of uncertainty. You know, we don't really know if what we said was understood by the user or what the user actually said, what they meant, and all of these things. So we need to model uncertainty into the environment if we hope to create more robust systems and more robust policies. And so here, instead of having a state, we have a probability over all possible states, and we call that a belief state, and we say, you know, we think that we are in this state, but maybe we are in this or that state, given what the user has said. So just to give you an example, if you have a conversational agent with speech and noise, the user says, I'm flying from Austin. Again, we have language understanding, and we have our hypothesis with our scores. And so then in the state tracking, instead of having one single state that captures what has been said so far in the dialogue, we have a set of distributions for every slot over the values and this kind of represents, you know, our belief state, where we think we are in the dialogue. We can do the API call, and then the action selector, instead of taking one state that has, let's say, Austin and evening, takes distributions into consideration and then produces a list of actions with probabilities. So, you know, we probably are going to do this, but sometimes we may sample from this distribution to create the action. And this goes into the language generator that generates the text. And so just to mention one of the well-known systems very briefly. So this is called the hidden information state model. And the idea is that, you know, like I said, instead of having a traditional system with very well-known or estimated state, I guess, you have a belief that keeps track of all of these probabilities. And we talked about this. So the main idea of this model is that because it's very hard to solve, we can solve it in a summary space. So instead of solving it for all possible, you know, actions, slots, and values, because you can say to the user, you know, in order all of the combinations of the things that the system can say can grow exponentially. Like you have inform all of these slots and all of the values of all of these slots. So what we do is we kind of break the problem down a little bit, and we have the summary action space that can say something like, okay, do an inform here, or do a request, because you don't have enough information, instead of saying inform the price or request the destination. And so we learn in this abstract, in this summary space, and then instead of going directly to the, you know, to the language generation, we map back to the what we call master space, given the belief that we have. For example, we have a hotel that has 3 stars, and the system says inform. Now we have the record from the database that we know the value of the stars, and we simply take that from the record of the database and put it in the dialog act and generate the text. And that's how it used to work. Now, one of the things that were good with this model was that it allowed us to group states. This summary space allowed us to group states that have the same probability. So we don't really care, you know, all of the things that we don't know about, for example, we don't really care. We can just put them in one state. And this allowed for partitioning of the space and then making learning a little bit more tractable. So we would do things like inform the slot that has the value with a higher belief, so the thing that we are more certain about, or do a confirmation on the slot that whose it has two values with kind of very similar beliefs. And these are the kind of things that it would learn, and then of course we would map back to our master space and do the dialogue. And the way to solve that back on the days were with GP SARSA, which is Gaussian process. SARSA is a reinforcement learning algorithm that has a similar update, not exactly the same, but similar update to what I showed before. And basically we model the Q function as a Gaussian process. We have a kernel that captures similarities between states and actions. And this is good because it allows us to explore the space where in places that have high variance. And we can take advantage of the similarities to, let's say, do some kind of transfer learning or something like that. But the disadvantages are that it doesn't really scale and it requires a lot of memory to run. Now moving on a little bit because I need to move a little bit faster, I guess. So another thing that has been done is multi-domain dialogues. So far I've talked about systems that can talk about hotels, but we may have multiple domains. It's not reasonable to have a system that talks about only one thing. And here is an example there. It says, hello, how can I help you? What appointments do I have tomorrow? And so on. And you see we have multiple domains coded with different colors, but the domains can appear in the same sentence. So like, I have an appointment tomorrow, and can you schedule a taxi after my appointment or in time to get the appointment, and so on. And so we can model the conversation as having multiple topics, and each topic corresponds to an ontology or a database, a knowledge base or a database. And depending on the model, one of the challenges is if we talk about hotels and we have a bunch of hotel domains, then if our belief state is very big and has scheduling and hotels and restaurants and all these things, how do we take the relevant parts of the belief and use that only in the hotel model instead of everything, just to make learning more tractable? And one of the things that have been done here is to model, I guess, to solve the general problem. So how do we do information seeking? If we have a database, we don't care about the domain, how would we go about asking for slots and values in order to solve, to bring up interesting items, right? So what we do here is, again, we have summary acts that are, we give the slot the value that has the top belief, maybe the second, but we don't really care. And we define a set of features of the state action space, and we learn on those features, on this feature space, instead of learning on the actual in-domain kind of space with states and actions and things. So we have features that describe how many values a slot has in the database or in the results. Like we want to capture things like what slot do we need to get information for next, so that the results in the database will be reduced a lot, so that then the dialogue can be shorter and we can bring up interesting items. So we can keep track of entropies or these kind of features that say, if this slot had a value, how many results would we get, and a few other things. So this allows us, instead of needing data to train a system for laptops and then another data set to train another system for restaurants, we can use data from laptops to learn this abstract model in this abstract space, and then directly apply it to other domains. And we can use the same principle to create a multi-domain dialogue system. So we have a dialogue system that has a single policy model and can talk about all of these information-seeking domains. And the idea of this work was that we define these communication functions like hello, buy, inform, select, that all of them are relevant in slot filling. And we design our policy network to get input. This is called domain-independent parameters. So we extract these features from the state and the action, and we basically learn on this feature space. And our policy, like I mentioned before, is to select, L is the slot, so we do an argmax over the slots and actions, and we basically pick what action is the best to do that will give us the higher reward at the end. Yeah, so these are this is the generic policy model that we can directly apply even without data on new domains with new databases. Okay, so we saw how we can do dialogue policy learning a little bit. We'll see a little bit more in the next section. But suppose that we have now an intent that the system has decided it's good to say, then we need to generate the language. So the most commonly used way to generate language is template-based. So let's say that the system produced this intent. So to inform the user that this is a nice restaurant at the center of town and it is expensive. So then we have all of these templates, and we need to pick one of the templates that best realizes the intent and fill the blanks with the values that we get from here or from their belief state. Other methods traditionally had many more steps, like content planning, differing expression generation, surface realization, and again it depends on the application. If you are building a transactional system, it doesn't really matter. You maybe prefer templates so that everything is kind of well constructed. And of course nowadays we have statistical models to do generation based on neural networks. So one of the ways is to do kind of a classification problem and let's say pick the best template of these. The other approach is to generate every token of the sentence. Now, if we add speech to the application, we have a whole other set of problems. Besides one extra layer of processing and picking up other people, we have other phenomena that we need to take into consideration, like turn taking, when does the person stop speaking, when does the system need to speak, how many milliseconds to wait, and all of these things, what's an acceptable delay and what is not, and multi-party conversations, multimodal conversations, if we have videos or other things, or screens and things. So like I said before, I'm just presenting a broad overview because there's not enough time, but I wanted to tell you about kind of other challenges that are more relevant also to how we synthesize the speech. So these examples are taken from Hatim's PhD thesis. He did it in France, if I remember correctly. So let's say, dialogue turn is one person speaking, and in spoken language, it's not as clear-cut as it is in text, that this person is speaking and then the other person is speaking. In spoken language, you just have a signal, and you need to say, which parts refer to this user, which part refers to the other user. And of course, people perceive overlap or barging differently based on different cultures. So some of them may be acceptable to have shorter delays or bigger delays or so on. So, some examples here. Hector can say, I would like to try some exotic destination this summer where I can, and then Tanya just barges in and says, have you ever been to India? Now, of course, it depends on the relationship between these two. If she was like an agent and this was a client, maybe it's not very polite, but if they are friends, maybe it's okay to barge in. Other problems, like here, I want to book a 6-person table tomorrow at 6. I hope it's possible since I have, sir, no problem, can I have your name, please? So again, depending on how this is said and how this is perceived, this can be impolite or polite or efficient or inefficient. And similar examples here, like we have apple juice, tomato juice, oh yeah, that's my favorite. So here, my favorite is probably tomato juice because that's when the user did the barging. So this is also very useful information that we need to keep track of, right? And so he defined a lot of types of bar genes. One of these interesting types is what we call a back channel. So while Hector is talking, Tanya is not exactly interrupting, but just showing that she's paying attention, or understood, or misunderstood. So depending on how we do these back channels and how we say aha, we convey that information. So it's okay to continue, or I didn't understand, please elaborate, and so on. And again, these are maybe trivial for people, but to design a machine to do that, it's a very hard problem. Again, another back channel, it can be a little bit more, just disappointing, but it doesn't mean that this user, Tanya, wants the turn. She just expresses some feelings, and then, Hector continues. And then another example here, where this is a system that the users call to dictate the numbers, a research system, I guess. So the user says 01, 4, 5, there's a short silence, system repeats, 65, 79, short silence, and then 67, 79, the user budges in, no, 65, 79, there's a long silence, system realizes, and so on. And so the length of the pause sometimes matters, maybe in other examples more than in this example, but this is something that you can control when you are synthesizing the speech, and it can have many effects into how people perceive the content that you want to convey. And so the way to go about this is to cut down the dialogue turn into micro turns, so shorter kind of time units. And we have some actions. This is just, for example, right? Like take the floor, release the floor, barge in, and so on. So when this is the scheduler, let's say it's a system that listens to audio, or maybe intents, or maybe both, and decides when the system should release the floor, so let the user speak if the user barges in, or when the system should take the initiative and interrupt the user, and so on. But to support this, it's important that the system has incremental processing. So if the system is producing, speech and the user barges in, the system has to have a way to understand that somebody is talking to the system, so the microphone needs to be listening, and then all of the components need to be able to receive the signals to stop the speech that the system is producing. So we need an architecture similar to a blackboard architecture, that, maybe this is a controller and not a blackboard, but we need, let's say, a controller that can listen to speech, and then let's say the user barges in, and our policy is to, whenever the user talks, the system will stop speaking. Then the controller needs to send signals to whatever is being generated. So if the system is talking, then this guy needs to send a signal to stop speaking. If content is being generated in a language generator somewhere, I guess there, we need to stop the generation. Or if the user is making a correction, then we probably need to stop the understanding and redo, or make some adjustments. So these are some other examples of how can we handle the input. And these guys proposed a kind of a buffer layered processing. So the write buffer is what goes into the next stream. So if the user is dictating, we can have the output. If we detect an error, then we can revise the output, and so on. But the interesting thing there is how do we handle this input, right? So there are 4 examples here of what the system can do, depending on which state it is in the generation process, and what strategies it can do to make it feel kind of seamless. So if the system is here and says you're right, and then a signal comes for repair, it can directly go there, or just go to they are blue, right? If the system has already said you are right, it is blue, then if it is in this segment, it will need to go sorry and say you are wrong, kind of repair this segment, and so on. But if it happens to be here, it doesn't do anything, it just flips there and says that. So there's multiple strategies, multiple things, and this is not a trivial problem. Other challenges are multi-party dialogues. So what if you have 3 people talking to each other, and maybe 2 people are very strongly engaged and one of them is left out? How do you handle this situation? Now, traditionally what we do is we would go and monitor how people take the turn. So do they look at each other? Do they speak at each other? You know, if you want to talk to one person versus the other, what do you do? And the system needs to keep track of this. And there's ways to go about this problem. This work used, I forgot the citation in this. It's Yoichi Matsuyama's work. And this used, he built this robot to be a facilitator. So whenever it detected that this guy was left out, what it would do is engage into the conversation. So try to find a point in the conversation of these guys here, and inject itself in the conversation. And then when the robot and these 2 guys were talking, then the robot would ask this guy a question. And so trying to bring this guy into the conversation. But you can imagine this may sound simple, but there's a lot of things that are involved in all of the, I guess, the whole pipeline, right? From speech generation to understanding to knowing when you can barge in and to understand which of these guys actually said what, or to understand that this guy has been silent for some time. And some other things, I guess. Yeah, eye contact is important for turn taking. For example, if you're talking to someone and you want to hold the turn because you're thinking, you probably avert your eyes. So you look up or you look down or you look somewhere, but not at the person, to indicate that you need to think and say, you know, have more things to say. And these are very important in conversational agents, of course. And like I said before, user expectations are important. So, you know, if we design an agent that looks very human-like, then users will expect the agent to have these capabilities kind of de facto. They think that the system should understand to barge in, or, you know, why is it a hard problem, or why doesn't it see that I'm talking to the system and thinks that the other guy is talking to the system. So, you know, there's a lot of challenges. And yes, other devices. And the hardest challenge perhaps is that if we want to train the system and we want to get data, a lot of the times there are very subtle cues, right? So subtle and sparse. So you may have 2 people talking to each other for an hour, and maybe you have like 3 examples of the feature you are looking for. And these 3 examples are very subtle. So how do you train a system? And these are some examples of some older and new, I guess, yeah, older systems. So this one would talk about shapes, so it combines some of the modalities. This guy is called Alex and would play with kids, designed to be gender and race neutral. So the idea is to get kids engaged with math. And this is a bartender that is embodied and needs to keep track of these 2 guys and handle the turns and interruptions and see whenever somebody wants to make an order or not. Okay, so far I've talked about mostly simple transactional dialogues, and mostly from a dialogue management perspective with a little bit of other intuition. But you know, there's other kinds of dialogues. And dialogues that may not have a goal, so your goal being to book a hotel or book a restaurant, maybe you want to design a companion, and your goal is to just be able to talk to the robot. And you want to talk to the robot or your assistant over the long term. And you know, these will become, I think, more important as assistants like Siri or Alexa or Google Assistant are becoming, you know, they're just there everywhere in our lives. So, you know, you will become to expect that the agent remembers what happened a year ago or 2 years ago or 3 months ago. So let's talk a little bit about socially skilled conversational agents and see, you know, I'll walk you through a project that I was involved in to see what it takes to design such a system. So a regular, not regular, I guess, conversational agent that doesn't have social skills, like I mentioned, has a part that does cognition or AI, and then there is the world, like what do you care about? There's a database, there's a car, there are things that you can do. So the agent interacts with a human, thinks a little bit, and then maybe moves the car, or washes the dishes, or brings up a new movie and something like that. To build a socially skilled conversational agent, you need a whole other layer of modeling and processing. You need to be able to model social behavior. So what does the user mean when they do something? How do you actually convey the system's intents in a way that is perceived the way you want it to be perceived? Like, you want to make a joke, how do you make sure it's not sarcastic? Like Alexa, for example, one of the things that they want to care about is not saying bad things to kids. And what is like an inappropriate thing for a kid could be that, Santa doesn't exist. How do you track that? It's not like, swearing or whatever. And it's other kind of things that can be very sensitive. If you have a robot, it's even more important. And of course, the context, like is it a meeting assistant? Is it your personal assistant? Is it in your car? And the culture play a very big role in how you make this agent. So for example, what we wanted to do is build an agent that can have a long-term relationship with a user. We had two goals, two projects. One was to build a tutoring system that would be with children for, say, a semester. And through building, because these have been proven again in the humanities, if you build a good trusting relationship, this would be a peer tutor, not a teacher. So our agent was also a kid, and it would help the other kid learn math over the course of a semester. And the other one was a personal assistant. So in these kind of settings, context matters, and context over time. So if we want to build, like, you have a person that interacts with an assistant over a long period of time, and of course you have also time in the sense that what has happened in the dialogue, in the life of the person, what has happened in the world. So the agent needs to have a sense of all of these things, but we won't focus on this right now. We'll just say what happens in the human and how we can actually build this kind of relationship. So the thing that we used and that we had a lot of support from studies and theories is rapport. Rapport is something that you have with someone. Could be a salesperson tries to build good rapport with people who want to sell cars to, or with a friend you have good rapport. It means that you understand each other, you click when you talk, and everything kind of flows. If you have bad rapport, it's like with people you can't really communicate with. It's kind of weird and awkward and stuff like that. So we wanted to model this phenomenon in children interacting with our agent. And like I said before, it's very hard. We had about 60 hours of videos of kids talking to each other. We had 12 kids, 6 boys, 6 girls in pairs, and then half of them were friends when they joined, half of them were strangers. They interacted 1 hour per week for 5 weeks. And so, we had these 60 hours, is not a lot. For the people, for the kids that were strangers, some of them became friends. So we wanted to see, how did they do that, right? What topics did they discuss? What gestures did they make? What jokes did they make? How receptive were they? This kind of cues paired with the theory that has been, done in the humanities for many decades to build computational models. And of course, this was very sparse data and very hard data, but we were able to do something. Up to that time, rapport had been misinterpreted mostly as being helpful or polite, and not viewed in a situational or cultural context. So it would be like one model kind of fits all for all kinds of relationship, personal or otherwise. But rapport is not always being polite. If you are polite to a friend, it creates a distance rather than bringing you closer to someone that you know. It's not always being explicitly helpful. it fosters unique conversational patterns. So if you take two kids that talk to each other, they are very rude, they're very direct, they tease each other a lot. And this means that they want to prove to the outsiders that they are, a closed social group. And, swearing at each other is okay because they are very close. So they want to express that by, doing it. And other forms of communication, common jokes, inside jokes, and other things. And it has been shown that it can be built and demonstrated with technology. People tend sometimes to assign personality to things, and so, this helps a little bit. So a couple of words on the theories. So we have three main, let's say, variables. We have mutual attentiveness, which means how attentive you are to the other person, how present you are when you talk. Positivity, which is how positive you are, how polite you are, receptive, and all of these things, and how coordinated the conversation and the whole interaction is. So over time, this is how important these variables are, and this is the stages of the relationship. So, you meet someone here, and then you get to know them, and this is, I guess, the plot when you become friends with someone. So attentiveness is always important. If you're not attentive to somebody, then, the relationship would kind of go downwards. But positivity and coordination are kind of have kind of an inverse relationship. So in the beginning, you are not very well coordinated because you don't know the other person. You don't know what they like, how offended, how what makes them offended, and all of these things. And you are very positive. But as it progresses, positivity drops, and as you become more comfortable with the other person, and then coordination increases because you get to know each other, right? So there's a few other things. These are very broad categories. Face management is, something, for example, you want to say something like bad news to somebody or something that will make them feel bad. How do you say that in a good way? Or, you can do that in a bad way. But, this is mostly what face management is, and how you save your own face, how you think other people perceive you, things like that. I won't go into many details, but feel free to ask. Right? Then some other more technical challenges, I guess. There is an uncertainty over the effects of the actions. So let's say that the agent wants to make a joke or wants to say something in a positive way. How do you know that it doesn't come out as sarcastic? How do you know that you do something now? And some of these things are longer. We call them conversational strategies, so they may span a few dialogues. So that your goal is to build a relationship. It won't happen overnight. You have to make a plan. But how do you know the effects that these actions have, right? And of course, there's this locutionary, pre-locutionary acts, which means what is the exact kind of face value content of what you're saying, what is it that you intend to say, and what actual effect this had on the other person. A ton of nonverbal behavior, like, where they look at, how much they smile, is it a fake smile, is it a real smile, the hands, the pose, how animated they are. And a lot of the times this is also has to be sort of normalized to the person. So some of them are more animated, some of them laugh differently, So these were all very, very difficult things. Not only to annotate, it took us years to annotate, and then train models, which are very sparse, and then also technically, so how do you actually build this agent and this synchronization and all of the timings to be, not perfect, but let's say acceptable. So I won't go through this, but I'll just give you the idea. So Ran Zhao did this work. So he went through a lot of studies of human-to-human interaction, of how people build, maintain, or break rapport in their relationships, and he came up with this model. So on the top is the goal of rapport, to enhance or maintain. So to maintain, if you've already have reached a level that you want. To break rapport, primarily wanted to detect when the user would want to break rapport to make repairs. And as you move down the tree, you have other kind of social goals or social theories, and at the leaves of the trees, you have conversational strategies. Like mutual self-disclosure means to refer to something, to talk about something that's about yourself, and then if you say to someone something about yourself, they tend to do the same. So it's mutual. So you can initiate it by saying, you know, hey, I'm Alex, I do this, and then the other person will say, hey, I'm George, I do that. You know, there's this kind of effects. Praise or negative self-disclosure, like, you know, I suck at math. If you want to teach math, you know, don't worry, I suck at math too. Adhere to interpersonal norms. So, and all of these things are not very constant, right? So adhere to interpersonal norms means you have a certain relationship with somebody, and this is governed by what we call interpersonal norms. So the way you usually interact with this person, and it's different from person to person that you know. If you adhere to it, it is good. If you break it, it is bad. It doesn't mean that adhering to it means polite or not, means adhering to the specific relationship you have with this person so that you are familiar to them. You don't seem kind of, you know, acting weird. Anyway, this is a flow chart of the interaction. So I mentioned briefly sometime before that we have discourse obligations. Like if I make a question, there is an unspoken obligation that somebody should answer this question. Otherwise, it may be perceived as, you know, impolite. So here we define the social obligations, which is, you know, let's say we have a way of tracking rapport. It was hard to do, but, you know, we did like a basic system with our annotations, and then we defined social obligations, like if given that we want to build rapport and make a good relationship, and the other person does a self-disclosure and says, you know, hey, I'm not good at math or something like that, then in order to fulfill our goal, we would initiate a strategy, like do a negative self-disclosure on the agent side as well. And so we broke down the interaction into two parts, the task part and the social part. So, you know, in this hour that the kids would interact, there are very few spots where they do social talk. A lot of it is just math. They were, you know, doing math exercises. So a big chunk of it, the biggest chunk of it is doing math, and a small piece is doing social stuff. So we had, a lot of the time, we just needed to just go with the task. And let's say rapport capital means that, you know, you want to point out a mistake. Do you think you have enough rapport to just say, hey, what you're doing is wrong? Or, you know, if you don't have it, how are you going to say it? Are you going to be direct? Are you going to make a joke? Are you going to say, hey, don't worry, we'll figure this out? And these are the things that this social reasoner tried to capture. So given the capital and the goals, come up with a good strategy to realize the behavior. And we made a prototype of this on an Android phone. And back then, you know, we couldn't charge it fast enough to render the graphics, so we would have it plugged in and the battery would drop, but, you know, we managed to shoot a video. This was a demo vision video. So a lot of these models were there, but some of them were trained on other data, or some of them were just rules that we had extracted from theory from our model. So given that we had the conversational strategy recognizer and a rapport classifier somewhere, you know, some of the other things we could just hard code for this demo. The hardest part, of course, one of the hardest parts was synchronizing the agent. So, you know, we didn't do incremental processing, but still, if you have your 3D system and your text-to-speech, you have a controller here. So here, you want to fuse, the colors are kind of bad, but this says language generation and nonverbal behavior. So we would fuse the two and create an annotated language that had gestures in some kind of markup language that exists. And this would be go into this engine that would render the 3D body and the speech. But so it would handle kind of the lip syncing, but maybe not the gestures. So, you know, we had a lot of things there. These are the projects that came out of it, and I can show you an early demo, and then oh, I can show you later. Okay, so I will show you the demo that we showed at the World Economic Forum. So this is Sarah, and this is a later version of the project. I had left the team, I guess, but the main concepts are the same. This was in collaboration with Yahoo and Xiaomi.
Hi, I'm Sarah. It's such a pleasure to meet you. Might I ask your name?
Hey Sarah, my name is Fedi.
Nice of you to take the time to stop by.
I think we used F-Lite for it was. So here we see that it's tracking the conversational strategies and the social variables, and it decides what to do.
Great. Well, let me introduce myself. I've been asked to play matchmaker by helping attendees find sessions to attend and people to meet, based on their interests. All you need to do is tell me a little bit about yourself and what you want to do while you're here.
So I'm a master's student at Carnegie Mellon University in the computer science department, and my research focuses on artificial intelligence and natural language processing. And I'm mainly here just to network, meet people in kind of the tech scene, and maybe go to some interesting sessions.
I've never met someone like you before. It's refreshing. This is my favorite part. Let's see if we can find some interesting people to meet. Just 1 minute while I look this up.
Sí,
There
aperto her
are
eye.
details on the screen about Justine Cassill. I feel you share some interests.
Yeah, Justine Cassell. I've heard of her. It would be nice to meet you though.
I can either send a message on your behalf suggesting a meeting, or I can give you the information and you can set up the meeting yourself. Would you like me to send the message?
Yeah, please do.
Oh, good. You'll see a message from me in your top link private message inbox introducing you to.
Awesome.
People have asked me a number of times why I wanted to work on social AI and what gave me the idea for this project.
Started to really see that human communication is a lot more complicated than exchanging words. Timing is very essential. Hidden meaning in words is very important too. And then we use the acoustic. For example, we should know the tone of the voice of the user. We use cameras to capture your facial expressions, and there are 64 landmarks in your face. These are things we really have to keep in mind when we kind of continue through our development of Sarah.
The Articulab represents the intersection of language technologies, human-computer interaction, as well as machine learning and psychology. Come together and work on interdisciplinary projects that look at the social aspects of technical design.
Is one of the examples of the bright future of artificial intelligence.
Sarah, standing for Socially Aware Robot Assistant, is your personal assistant, so she can recommend interesting sessions, interesting persons in this Davos conference.
In this era of fears about robots taking over our jobs and killer bots, I really want to highlight the role that robots and agents can play as collaborators with people, as partners with people, instead of taking over for people.
Okay. 1, 2, 3, smile.
So you get the idea. And, these things will become more and more relevant as the rest of the technology, I guess catches up. I mean, the rest of the technology, the conversational agents become more prevalent, they can do more things, they can understand better things. So the social aspects will start becoming, more important, like the Alexa weird laugh that was, I don't know if you guys know, about a year ago, Alexa devices just started laughing weirdly because they just heard the sound that thought it was a command that said Alexa laugh. So it would just laugh in the house, and many other things. Questions? Okay, we can take a break and get back in about 15 minutes for kind of more current.
I have a question. In the last video you showed, I saw that the agent was speaking like a neutral way, and the communication is in both ways. And so if he tries to recognize and get more personalized communication with the person, how it can work in that way.
You mean speaking neutral?
I just felt that the agent was speaking very just neutral.
So we had this problem with how to synchronize the TTS, and this was a university project, so not a lot of funding. So when I was there, we used a flight, which doesn't have a lot, very good quality, but it gives us a lot of flexibility of how to synchronize it with the lips and the rest of the system. So it was a lot of technical challenges that we had to overcome, I guess. And this was the best voice that was probably available for that. But yeah, I agree with you. It doesn't, if it's neutral, yeah, it's...
Yeah, okay.
Yeah.
Okay, thank you.
In this part of the talk, I will introduce a little bit the deep learning in dialogue systems. Again, because there is not enough time, I will talk about some of the approaches to some of the problems that we have been facing and what people have been doing with deep learning. So there is a few ways that we have been using deep learning. For example, the easiest thing is to just replace function approximators, or replace entire modules with neural networks like language understanding or dialogue policy, or replace everything with a single neural network that goes from text to text, and you have an agent that can receive text and produce your response. And of course, there's many challenges and opportunities still ahead for most of the problems that I mentioned before. So, a lot of the times networks can be very hard to train. Some of them are very specific to applications or datasets, so there's not really wrong architectures. So I'll just, show you a few examples of some interesting things that are, most of them are very recent. So for language understanding, traditionally there's many topics like parsing, named entity recognition, slot tagging or intent detection, topic detection, and many other things. And nowadays, we usually do this with deep learning, some of them explicitly or implicitly. And there's some interesting models that I wanted to talk about before going into the dialogue. Now, I'm not, you probably know more about these than me, you're probably using them more, but I'll just talk about the general ideas. And then how people have been using some of these things on later parts of the pipeline. Yeah, and some models can implicitly learn these, or they are explicitly trained on these to boost performance. So something that helped dialogue systems a lot is, of course, word embeddings, where the main idea is to have a numerical representation of words, and that allows the model to learn and allows us to do meaningful calculations in this semantic space, like in these examples that they have, king and queen, or I don't know, book and hotel, or apple and mango, or apple and windows, and things like that. So the idea is we represent each word by a vector, encoding the semantic information in there. And there's two main kinds, frequency and prediction. Frequency, I guess, is the older ones. I'll just go over it quickly. So the idea is we have a list of documents, which is our corpus, and a list of terms, which could be, let's say, words that we care about. And we can do things like count how many times each word appears in the document. We can do TF-IDF, which is term frequency and inverse document frequency, which kind of penalizes common words. Or co-occurrence, where it's the number of times that two words appear together in a context window of sentences that we have in the corpus. And basically we end up with a matrix that has some representation for each word. But these are not always very meaningful. And so the prediction-based embeddings is what gave a big boost to dialogue. The colors are not very good, but it says quick brown fox jump over the lazy dog. And there's two main kinds, I guess, continuous back of words or skipgram. So the main idea is how can we capture the relationship of a word with other words. So we can either predict this word given the context or predict the context given the word. And if we train a network to do that, then we can get the one of the hidden layers to be our representation of this word, because this captures all of the information that the decoder needs from the word and the context. And so, we assume that this is a good representation for each word that captures these semantic relationships, I guess. That's the overall idea. Now there is a problem that we face sometimes, that when we have our corpus of sentences, each of the words is used exactly within the context, but when we try to query the model, we use it in a context-free way, as in, we have one representation for bank, and this can be open a bank account or on the river bank. And if we have a single vector representing the word bank, then this can be problematic. So one of the solutions is to train contextual embeddings, which means that bank will have a different vector given the context. So one of the models is ELMO, embeddings from language models. So the idea here is to pre-train bidirectional language models on a variety of tasks, like natural language inference or sentiment and other things. And so bidirectional means that we look at the sentence in the forward way and also in the backward way, I guess forward and backward. And then we train the model and we use, again, latent layer as our pre-trained embeddings. After that came the transformer. Let's say this is, I guess, an important architecture. Let's say that we have a model. This is taken from this very good post, all of the illustrations. So, you can also read it, you can read the paper. Let's say we want to make a translation from French to English of I am a student. So we have this model that can actually do that. Going a little bit deeper, we can see that this model has two parts, a part composed of encoders and a part of decoders. So encoding the information and then decoding all of the information encoding what this means and decoding in our target language. So here actually we see that we have stacked layers of encoders and layers of decoders, so we do this multiple times. I think 6 is what they used in the original paper. And inside, going a little bit deeper inside, we have this self-attention, which is, I guess, the core feature of the transformer. So we have the self-attention layer and then feed-forward layers. And this is one encoder layer, and it repeats many times. And in the decoding part, again, we have self-attention, but we also have some attention that comes from the encoding layer and then feed-forward. So this means that, whatever this guy wants, whatever the encoder thinks that the decoder should pay attention to given, the input. And so why this is important, self-attention means basically that, every word in the sentence, let's say we have a sentence, the animal didn't cross the street because it was too tired, then every word can pay attention to all of the other words, including itself. So if we train it properly, we can model relationships between the words that can be very useful for our task. So for example here, it, has some attention to the animal and a little bit less to other parts. And the way this works, again, kind of roughly, is that if we have an input, let's say 2 words, the idea is to calculate a score between this word and itself and all of the other words. So we have queries, keys, and values that are just vectors, and we have matrices there with weights. So for every word, to calculate a query, so basically what we do is we want to take the product of the query and the key to calculate attention, say, between thinking and machines. We will take this query and this key and calculate the product, and then some normalization with the value and add everything up. So to calculate the query, these are trainable. Everything here is trainable, right? So these weights, given this word, will learn what is a good query for this word. And these will learn what is a good key and the value of this word. So the product of these or of these here, let's say it's kind of like the attention that we give to the value of machines. So very roughly, this is how we can calculate it. And if we, if we train it, then we can get a score for thinking or thinking and machines. This is, I guess, normalization, and we get the softmax and then add everything up. So this gives us some attention over, the words, but then another feature of the transformer is that we can have multiple heads of attention. So we can learn different ways to do queries and keys and values. So we attend to different things. So, as we would do in language processing, like what does this refer to, but also, tired and things like that. So every head can attend to a different set of things, I guess. One could be like what is the object or whatever other thing that we are interested in. And the important thing here is that there's no locality bias, meaning that if you had, I don't know, LSTM or maybe an RNN, it's hard to model the dependencies in the past, but here we explicitly attend to all of the inputs, and so this makes it less biased to, what word is close to you at this point in time, and we can handle sentences better, or longer sentences. Of course, I presented a very rough
Excuse
idea.
me. I didn't really understand what keys and queries are.
So, so here we need to calculate a score of how much this word should pay attention to this word, right? So the way that we do it is we calculate a dot product of this. So we take the query of the word. So we train the weight matrices, I guess, to say what for this attention head, let's say, we train this weight matrix, and this query refers to this word, and then this query will be multiplied by all of the keys of all of the other words. And so it calculates a score of how much attention to pay to the value of the word. And all of this is trainable. So then they can learn different patterns, I guess. And, this guy will get its query and multiply with all of the keys of all of the other words, including itself. And then this calculates a score of how much attention to pay, and we multiply that with the value of the... Yeah, okay. So, we can end up with different levels of attention, let's say, to different words. Yeah, so I guess it's a little bit more complicated, but we also pass some attention from the encoder to the decoder, just to say, to pass some information into what parts of the sentence the decoder should also pay attention to. And this is their illustration. of how you do the translation. So in let's say this is a single one of the layers, and we pass the attention, the keys and values from the encoder to the decoder, but the decoder also has its own attention. Then came the generative pre-trained transformer, the GPT from OpenAI, which is a multi-layer transformer decoder. And what it does, they just stack up a lot of decoders, and it had a lot of performance in very many tasks. And the good thing about this is that because it's a unidirectional model, it is kind of better maybe for generating words, so it can predict the next words of a sentence, so it can generate text, and that's why they have all of these examples of, you give it a sentence and it creates some stories or something. And they also did some byte per encodings, which I think, again, I haven't used this myself, but my understanding is that these are some of the best encodings. Just, they decompose the word into word parts with some tokens in the beginning. But anyway, just saying the main ideas here. The main idea is that you pre-train your GPT or your transformer on a lot of tasks and a lot of data, and then you only add a small layer on top for your specific task. So you can download pre-trained GPT or anything of these models that are trained on big data, and then fine-tune on your own application. Another model is BERT, which basically is bidirectional, and this performs very well. So it's similar to GPT, but it's bidirectional. And the way that they trained it is they mask some words. So it's a little bit of complex procedure how they do it. But basically they select a percentage of words in the sentence that they can mask, and then they replace that with a token, and then the model has to predict that token. And in doing so, it learns better representations and where to pay attention to, and better representations for the words. And also sentence prediction, like, for example, entailment. If given the evidence, you can, the other sentence kind of follows. Of course, it has more parameters because it's bidirectional. And then ExcelNet came after that. So one of the problems with BERT is that, so you train your model with masking, but then maybe you don't have that when you're doing fine-tuning, and it makes some assumptions of independence of these masks, I guess. So, you can, I think there are works that use BERT as generator, but you can end up in a situation like this, like the model can say, I went to New York and saw the Empire State Building, or I went to San Francisco and saw the Golden Gate Bridge, but this doesn't make sense. I went to San Francisco and saw the Empire State Building. So these were the things that the model didn't capture, I guess. So ExcelNet did something different. The main idea is that they have permutation language modeling. So the main idea is that you have a sentence and you don't predict each word sequentially, but you predict, say, the first word and the seventh word and the third word and the fourth word and so on. And, this is BERT. You have this input. You need to predict this output. Then you have this input. You need to predict this output. This is masked. You can predict this. But then with ExcelNets, you need to predict. You don't predict sequentially, basically. You have the sense of the position. And this gave a bigger boost, but also, talking to people who have used them, I see that it's a lot harder to train, more parameters maybe. So maybe BERT is a good compromise, and I know that BERT you can get pre-trained models, use your corpus, have a small layer on top, and use it just directly. So these are very important models in dialogue. That's why I mentioned them. Yeah. Now I'm going to focus a little bit more on the specific parts of the dialogue system and how people have been using neural networks in general to solve some of the problems. So, for example, for intent detection and slot tagging, the idea is you have a sentence and let's say this is flight booking, you have the intent to get the airfare, and then we have these tags. So the tags are called begin, in, and out. They are very simple tags. It means that for every slot, let's say we have class type and from to, for every slot we have a B tag, an I, and an I tag. So if it is a phrase like first class, then it will have BI. If it was a longer phrase, it will have more I's. And Boston, it just has a B, Denver a B, and everything else is out. So if we have a good model that can, given a sentence, predict the tags, then we know the values of this slot. So we don't need to, predict values. We just need to predict which words are values of the slot. And so typically what we do is we have a bidirectional RNN, and then it has two heads, one that predicts the intent, like simple classification from however many intents we have, which could be our dialogue acts. And then we have a tagger that for each word will predict the tag, like from location, O, or whatever it is. So for each word, it predicts the tag and the intent, right? And that's how we do language understanding. So for state tracking, things are a little bit different. We need to predict a state. So we need to keep track of what has happened so far in the dialogue and be able to, keep track of all of the slots and all of the values. And for example, these guys they call global locally self-attentive dialogue state tracker. This basically means that you have the global means shared weights between slots, and local means, not shared weights. What happens is, and this is an idea that you see a lot in dialogue, you have, let's say, an encoder that you want to use for something, and if you are in the hotels domain or if you're predicting the price range, you give a token for the price and the sentence. If you want to predict another slot, you give another token and the sentence. So you're kind of conditioning your model with the knowledge of what slot you're predicting. I don't like this very much because it means you have to iterate in prediction time, you have to iterate over all of these possible slots and get a prediction of whether, this is something or not. This is another interesting model that got good comments. This uses a generator for the state, which means like not a classifier, but a generator. So it will generate which slots and values are there. So what they do here is they have, again, a bidirectional encoder to capture the context of the sentence of the user. And then, like before, so this will calculate some attention and some context vector. And what this does is classifies into one of three things. Pointer, don't care, or none. Don't care means that, you say any kind of value, any kind of number of stars. None means that this particular slot wasn't mentioned. And this means that you get whatever the generator outputs. So again, here they have tokens for domain. This is a multi-domain state tracker. So they have tokens for domains and the slots. So they would, condition the encoder with, say, hotel and departure, and see if hotel and departure were mentioned in the sentence. And if it was, this will output this pointer or something. And then you will get whatever the state generator outputs. Otherwise, you discard it. Now, this is not, this is kind of just for illustration, because I couldn't find a better picture. But, you trained your dialogue state tracker, given a database, and then you put it in your product, and then somebody goes in and puts another restaurant or another hotel or another something. So you have a value that you haven't seen before. So there are ways, of course, to deal with this. One of the very simple things you can do is, if it doesn't exist in your ontology, in your data, you can somehow compute the similarity of this value and with other values that you have. Let's say if this is restaurants, maybe you have Mexican and Greek and whatever. So Italian is somewhat closer to that. So you can either use the food type network, or you can create a new tagger, and you get the weights of the model that is closest to Italian. And the same thing applies to unknown slots. So in this work, what they did was they had, I don't remember exactly which domain, but they had a lot of slots, and they went to Mechanical Turk and asked people to paraphrase the slots so that they can create embeddings for each slot. And then when they had an unknown slot, again, use the weights of the closest model for the slot. Let's say you have a model that captures destination, and then you have you've never seen origin in your data, or you have something else that has location, then probably the model that captures destination is very good for that. So you can just initialize your new model for location with these weights, and then train it a little bit. Moving on to dialogue. So there's a lot of works. Something that has been appearing again is model-based reinforcement learning. This simply means that you have a model of the environment inside your model. So, the agent wants to make a move. Instead of just making the move and seeing what happens, it queries its own model of the environment and says, if I make this 100 moves, what will happen according to my model of the world? And then select the best move. So you have a model of the world and your dialogue policy. You have some data to train these things. And then when interacting with users, you can get real experience, but you can also query the model many times, interact with user fewer times. And I guess in this paper they had another interesting thing that, you have a lot of shared representations for example, for different domains, let's say, or something like that. And then task-specific ones. Another concept is for reward estimation. So I mentioned before a little bit that designing a reward function is very hard for dialogue, because this defines basically, how you optimize something, right? And in reality, it's very hard to get feedback from people. You have to listen to other cues. And also, for example, here, we define, depending on how you define success or failure, if you see this example, the agent actually provided all of the information that the user asked for. But if the user never asked for address, then, why should we penalize the model? Which is like a traditional way that we have been defining success. So success is defined as completing the task. And the task is to request the phone number and the address after finding the restaurant. But if it doesn't appear in the log, if the person making the call just, skipped it, then, we would penalize this as a bad example. And this can have bad effects in learning, because it is actually a very good trajectory that we penalize in the end. So one thing that people have been looking at is how can we, given the data, learn a function that we can have our dialogue and estimate the reward, and then train our policy on the estimated reward. So here, they have an encoder-decoder, so they encode basically the dialogue, and they try to learn a model of the reward that is better than the reward that we give, that we kind of hand design. And this results in better interactions. Also, other works are getting acoustic features or other kinds of features, so that you don't even need to hand design, but maybe have a fuller set of features, like if it's acoustic features, you can detect, for example, sentiment or whatever the user is unsure, or things like that, and this can feed into your policy, provided that you have maybe like a feedback of user satisfaction or something like that. And all of these work that I have seen, there are not very many, but they perform a lot better than just a very simple task success. Other models are, for dialogue policy, a little bit more distributed. So here you have your belief state, And so this touches upon the problem that if you have multiple domains and you have a very big belief state that represents everything you know about the user and the dialogue, how do you pick, which parts are relevant for the current domain? And here they have this is similar to the domain-independent features, and they train smaller models that are, dealing with sub-dialogues, for example. Here, maybe they have the slots that have no arguments, and here the slots that have arguments and things like that. You can break it down in different ways. You can break it down in domains, or you can have hierarchical policies, and so on. Another interesting problem that we have been facing is how to create a SQL query given a dialogue. So you remember I showed before the hotel query and then intent detection, and then you make this SQL query. So how can we automate this process, in case of API changes, or in case of not only, just talking to a database and writing a very complex query, which is a very hard skill to learn as a person, but also, for conversational agents. So here, what they did is they defined a number of errors that usually happen when people do these queries from text, and try to estimate the error somehow, anyway, to account for that. So like if they forget to join, or I guess they didn't do very hard queries, but the system could ask the user some questions to make the query better and more accurate. Then there's other things that haven't really been used. This is an older paper, like neural Turing machines or differentiable neural computers, which like very roughly have a read and write memory. And so supposedly when they came out, everybody was very optimistic, but I don't think I've seen many dialogue or any dialogue paper that uses these machines. But the idea is, keep in memory stuff that's important. They have been doing copying images or other kinds of things, so why not use it in dialogue? And then language generation. So I picked this paper because there's another thing that I wanted to talk about. So what they do here is what they call semantically conditioned language generation. So generation conditioned on context, I guess. So they have LSTM encoder, and this is a variational autoencoder, so it means that roughly, in the middle layer you can sample from a random variable so that your language is not always the same. Like if you train your language generator to, let's say, from dialogue acts to text, and it sees a lot of data, sometimes it can collapse and produce this exact same language given the input, which is not something that we want for a dialogue system. You're going to have some variability, and so you can have the variable there to sample some randomness or some other, not randomness, but give it some variability. And here they use what they encode as prior, and they predict the domain, the dialogue act, and the slot. During of course, the words. During inference, they use a representation of domain, act, and slot that they have identified before in the pipeline. They don't use this, and they, use the words. So it's a case of, many times we see that you can train your model on multiple tasks that actually help another task that you're trying to solve. And, this happens a lot also in dialogue, especially for NLP. Other things include emotional language generation. So how can you create language that is infused with emotion? And here also they have images, and so they combine different modalities, so images and text, into something that says we had a great time at the beach. Also tying to what I said before, social language generation. So here, I was partly involved in this. We have a message that we need to encode, and we have some history, and we have some other information about the system and the current status of that person. And this is for onboarding drivers, and we have the documents, and then we can create the agent's response. It's a kind of simple architecture, but we wanted to see how social language would help the success rate of onboarded drivers, so drivers that go through the pipeline and start driving for some task. And so we have the same model, but we add some conditioning on politeness or positivity. We had a corpus, of course, that was annotated. And so, we can simply condition our generator on the social variables and create better language. But, that's only part of the story. So one of the hardest parts also is how do you decide how to condition this, like what these parameters should be at runtime. And these should be, provided by the dialog manager or by other social components. And here's another example of multimodal, I guess, that they fuse. And there's, of course, many others, visual QA, embodied agent, simulated understanding, house 3D, Matterplot, all of these things have simulations of homes, and you can talk about objects like how many cars did you see on your way from the bathroom to the kitchen, or, all of these things that you need to fuse multiple modalities. And the last section, I guess, is on joint optimization. So many people have tried to solve this problem of, annotation is expensive, dialogue data is very scarce, but we have a lot of text and a lot of text available on the web. So, why don't we make a model that can go from text to text without us having to annotate every single intermediate component, data for intermediate components, right? And so this is one example where, again, it is in the restaurant domain. You have your utterance and encode it. You somehow extract important parts that query the database retrieves some features. Features could be like, you have less than 10 results or less than 3 results or more than 100 results and things like that. And you have your policy network and your generator. I also wanted to mention this paper. This was from IBM maybe 1 year ago. So one of the problems that we're facing is how do you do database retrieval and how do you refer to other things in the dialogue? Like, you've talked about 3 restaurants, how do you refer to the second or to the, the one that had the nice menu? So what they do here is they have 3 layers of memory that they keep track of things. So they do their encodings, and then they have the first layer of memory keeps track of the query, which is basically slots and values. Maybe they get, the maximum, the value with the best belief, best probability for this slot. And this is the layer that has the queries. Then this is the layer that has the results. So these are specific hotels in this case. And the final layer is the layer that has the actual items, that is keys and values. So you have prices and, slots and actual values. So by attending to each of these layers, you can see if the user says something like, how much does this cost compared to the previous one? So you learn through this attention to attend, to go to the previous query and retrieve something from there and, say maybe, with a copy mechanism or something. And of course there are other architectures. This is hybrid code networks that attempted to kind of fuse API calls and programming with deep learning. Memory networks have been used somewhat. I guess so some of these tasks are not really dialogue, but I think in the more recent Facebook Barbie tasks, they are more conversational. So here you also have memory that you can, put your dialogue history into, or, API call results. Generative adversarial networks. So one of the things that you could do here is, you have a corpus of dialogues, human to human, and then you can train 2 agents. One is a user, one is a system, and they generate a dialogue, and you have a discriminator that says, this dialogue is human or this dialogue is artificial. So by kind of iterating, you can create your agents that produce good dialogues. And hopefully you can augment the data, basically, create new interesting data. This is, again, some work from our lab. It's called Flexibly Structured Dialogue Modeling. It's basically end-to-end on the Cambridge restaurants, and it's like a sequence of sequence-to-sequence models. It has an encoding part and some decoders. Again, here, the idea is that you condition the decoder with the slot name, and it brings you the slot, but these are actually shared weights. So I'll go over it a little bit. So you have your encoder that gets what the agent said, what cuisine do you prefer. It gets the previous belief state, and I guess what the user said in response to what the agent said in the previous turn. So this is the current user turn, the belief, and what the agent said before. And this goes into, this is an informable slot decoder and a requestable slot decoder. The difference is that for the informable slot, you also need to produce a value. If the user says, I want Italian cuisine, Italian is something that is meaningful and we want it, so you want to capture the value. If the user says what price range, how much does this cost, there's no actual value, there's only the intent of the slot for the slot price. So we kind of fused for the requests the intents and the slots. And so here, again, we get the encoding that came from before and condition the decoder with a token that represents the slot, and we get some values for each. The requestable slot is a classifier. We basically fuse the request with a slot. So we can predict which slot was requested, if a slot was requested or not, given the condition. We can do then a database query, and we get very simple features of how this is kind of a discretization of how many items we have in, matching the query that we make in the database. And we also, of course, grab the top item. So, and then the response classification is what action the system should do. And then there is this copy mechanism that we get whatever values are from the informable slot decoders, and generate the requestable slots and whatever the system should do. And this gives us an idea of whether we should copy something, from the input or from basically the database result, so that we can say it in the output. And then the generator, basically gets the last state of the encoder, what result we got, and which words we should copy or not. Any questions before I move on? I guess it was an overview of problems that we have and how we solve them. Yeah.
Are there any standard benchmarks for dialogue systems?
Yeah, there are standard benchmarks. There are some domains I mentioned somewhere in the slides. And then there's these information seeking or slot filling domains. But these are kind of simple for realistic applications. So there's challenges, the Dialogue Systems Technologies Challenge, used to be Dialogue State Tracking Challenge, that nowadays, people post challenges, so there's 3 or 4 running every year with different themes and,
okay.
scores. Okay, so now I wanted to talk a little bit about Plato, which is the dialogue system that we will use in the hands-on in the next section. So to introduce a little bit of what it can do. So this was released last Tuesday, I guess. So it's a platform for doing research and creating quick prototypes or demos. It's intended for researchers, for programmers, or hopefully soon we'll have a graphical user interface. But it's not a product platform, so it's not optimized for products. It doesn't have a commercial license even. It's optimized to have a very understandable and clean design. So what it does is it can talk to people, or it can talk to other artificial agents, Plato agents, or it can talk to data, which means that be trained from data. Zooming in a little bit further, Plato can talk over speech, over text, or structured intent, structured information like dialogue acts and intents and slots, and can produce speech, text, can do something somewhere, can train statistical models, and can produce simulated data. So if you run it in a simulation mode, it will create a corpus of dialogue that you can then use to train other systems. So zooming in a little bit more, this is the standard pipeline. So if somebody says, I'm thinking of burger, we extract the meaning, which again is the intent, slots and values. We have state tracking, that is the information so far in the dialogue. We do an API call, see what's there, select an action. So in Plato, this space and this space are the same, so in intents or dialogue act space. And then we generate some language that goes to the user. The user can also be a simulator. So we can be interacting with a simulator to generate more data, to train other models, and so on. Also, what Plato does is provides for this standard pipeline APIs or abstract classes that you can use to, if you write a component, let's say you have a new idea for a language understanding component, as long as you respect the I/O, which is not very, demanding, you can plug your own component there. And we'll see some examples of how to do that. Some basic functions is that you can easily create and run a conversational agent, and of course have multiple configurations. We can have multiple agents or interact over speech or text and so on. And also you can train your model offline with your favorite neural network and plug it into Plato, and if you respect the API, it will work. You can also train a module online using the algorithms that Plato provides, or write your own algorithms. Even Ludwig, which I will introduce a little bit later, provides online learning. Ludwig is a deep learning framework. Another basic component is the logs or experience. So as we go through the pipeline, Plato will keep logs of everything that has happened in the interaction. So every component in the pipeline can then use these logs to train, either online or batches or offline. So I guess the design is a fusion of the reinforcement learning and decision theory and dialogue theory. So it is geared towards reinforcement learning somehow, especially the experience that we keep. And so the actions are what the users or the agents can say. The states provide a representation of what has happened so far in the dialogue. And the domain is what we can talk about. The main things are the ontology and the database. The ontology you can think of as the schema of the database, more or less. So we have the core class is a controller. The controller initializes the dialogue. It reads a configuration that is a YAML file. It will initialize one or more conversational agents, and then it kind of orchestrates the conversation. So the controller will start, continue, or terminate the agent. The agent may have some of these or all of these components active, and the agent will expect input if it's interacting with speech or text, and will handle the API calls. And of course you can have statistical models trained in there. So in the hands-on later, we'll see how to create a conversational app. So the way that you start is, you have an idea, and if you have data, then everything is good. You can annotate the data, create an ontology, given the data, and train your statistical models, put them in Plato, and it works. But what if you don't have data? So then what you can do is come up with an ontology of something that seems kind of reasonable, kind of plausible. Let's say you're going to create an application for travel planning, and you're going to have cruises, hotels, and restaurants, and other interesting things. And so you put all of these things in the ontology, and you create a simulator. So this takes a little bit of work, but you can create a simulator that will try to simulate what a person wanting to book travel would do. So they would ask maybe for hotels, probably flights, and some experiences and things like that. So these are the behaviors you could encode in the simulator, and you can have Plato interact with the simulator, create simulated data. Then of course you can train models, but they will be weaker because they are based on simulated data based on the things that you created. But you can still train these models, have an agent, and then have this agent interact with humans, and so you create better data, better statistical models, and you can kind of loop over this pipeline. We talked about a domain. I guess the main important things are the ontology and the database for the slot filling domains that we work with. It's a collection of intents, slots, and their values. And like I said in the beginning, we have informable and requestable slots. And the database contains the actual items. So in Plato, as you will see later, there is a script that allows you to create this ontology and database given a simple CSV file. So if you have a CSV that has the first line is your column names and then is your data, you can just run the script. It's not very complicated, the script. So it will create the domain for you. So I've also put a lot of modules in Plato that are, I call them dummy because they are there for kind of sanity reasons, like to check something works, that the pipeline works. If you want to create a dialogue policy, train a dialogue policy, and you don't want to care about understanding, you can just use the dummy module, but it's not recommended. You should probably train your own model. Now Plato provides some user simulators, I think 2, but then more coming in the future. They can be rule-based or model-based if you train your simulator given data of how people talk to each other. One of the basic structures is the agenda-based. So you have your database and you sample a goal. Let's say you have like a food ordering system. So you sample a goal, and let's say these are the things that the simulated user wants. So the user wants Italian and wants pasta and wants to ask how much does it cost. So we have this stack, the agenda, and we put dialogue acts that reflect these constraints. We have constraints and requests. So we push inside the agenda dialogue acts that reflect this. So inform Italian, inform pasta. And of course, we have some other kind of actions like hello and goodbye, just to make the dialogue seem more realistic. And then whenever the system says something, we have either some rules or a policy that tells us what to push in response. So if the system says, what location do you prefer? This is not in here. So we would push an act that says location, don't care. And that would be popped, and the user would then express that in natural language. Of course, there's some consistency checks to remove duplicates or other things that will harm the dialogue fluency, I guess. And then we can sample from distribution or pop just the first action, pop 2, 3, or 1 act. Of course, you can build your own simulator and put it in place. I'll go a little bit quicker because I want to talk about Ludwig for 5 or 10 minutes. So the way that Plato works when you learn from data is you have your data and you need to write a parser. So the parser will convert the data into Plato experience that are states, actions, and everything, but this can be kind of a hard task. So an easier approach is to parse the data into a CSV format, and we'll see that in the other section. And then using that, you can train your model using Ludwig, which is a deep learning framework, and import that into Plato. Okay. Oh, I don't have the Ludwig presentation actually here. Let me see.
Okay, so thank you, Alex, again.